Hey, welcome to my channel Technologies in Industry 4.0. Today, in this video, I will discuss about the hyperparameters selection in deep learning. So, let's start the video. Hyperparameters selection in deep learning. Introduction. Hyperparameters selection in deep learning plays an important role in deep learning. Maximum deep learning algorithms come with many hyperparameters. Those handle multiple features of the algorithm's behavior. A number of these hyperparameters upset the time and memory cost of running the algorithm. Some of these hyperparameters disturb the quality of the model recovered by the training process. These also affect its ability to infer accurate results when deployed on new inputs. In this article, we will describe guidelines on how to choose the hyperparameters of a deep architecture. Description. There are two elementary methods to selecting the hyperparameters. Manually choosing hyperparameters. Automatic parameter selection. Choosing the hyperparameters manually needs knowing what the hyperparameters fix and how machine learning models realize good generalization. Hyperparameter automatically selection algorithms importantly decrease the need to know these ideas, though they are frequently much more computationally expensive. Manual hyperparameter tuning. We should understand the following points to set hyperparameters manually. The association between hyperparameters. Training error. Generalization error. Computational resources such as memory and runtime. Goals of hyperparameter search. The objective of manual hyperparameter search is generally to find the lowermost generalization error. That leads the subject to certain runtime and memory budget. The main goal of manual hyperparameter search is to modify the real capacity of the model to match the difficulty of the task. Real capacity is forced by three factors. The figurative capacity of the model. The capability of the learning algorithm to well reduce the cost function used to train the model. The point to which the cost function and training procedure standardizes the model. A model with extra layers and additional hidden units per layer has higher figurative capacity. That is accomplished of expressive more complex functions. The overfitting happens for some hyperparameters when the value of the hyperparameter is huge for certain hyperparameters. One such example is the number of hidden units in a layer. Increasing the number of hidden units upsurges the capacity of the model. The overfitting takes place for some hyperparameters when the value of the hyperparameter is small. For instance, the minimum acceptable weight decline coefficient of 0 matches up to the greatest operational capacity of the learning algorithm. Learning rate and training error relationship. Learning rate and training error relationship. The learning rate is maybe the most significant hyperparameter. Tune the learning rate if we have time to tune only one hyperparameter. It handles the active capacity of the model in a more complex method than other hyperparameters. The actual capacity of the model is utmost when the learning rate is accurate for the optimization problem. It will not be highest when the learning rate is particularly big or especially small. We have no choice but to raise capacity if the error on the training set is higher than the target error rate. We must include more layers to the network if we are not using regularization. This upsurges the computational costs related to the model. We may now take two kinds of actions if the error on the test set is higher than the target error rate. The test error is the quantity of the training error and the gap between training and test error. Automatic hyperparameter optimization algorithms. Neural networks may occasionally do well with only a small number of tuned hyperparameters, though frequently advantage meaningfully from the tuning of 40 or more hyperparameters. Manual hyperparameter tuning cannot work very well for many applications. Automated algorithms may find valuable standards of the hyperparameters in these cases. We understand that optimization is happening if we think about the way in which the user of a learning algorithm searches for good values of the hyperparameters. We are trying to find a value of the hyperparameters that enhances an objective function. For example, occasionally validation error under constraints. In standard, it is so possible to progress hyperparameter optimization algorithms that wrap a learning algorithm. Also to select its hyperparameters, therefore, hiding the hyperparameters of the learning algorithm from the user. Hyperparameter optimization algorithms repeatedly have their own hyperparameters. For example, the range of values that should be discovered for each of the learning algorithm's hyperparameters. On the other hand, these subordinate hyperparameters are regularly informal to choose. That is in the sense that satisfactory show can be attained on a wide range of tasks using the same secondary hyperparameters for all tasks. Grid search. Grid search. Grid search is a traditional method for applying hyperparameters. It is characterized by an absence of reasoning or intelligence forces altogether. Grid search needs to create two sets of hyperparameters. Learning rate. Number of layers. It trains the algorithm with a learning rate and a number of layers altogether. It also measures the efficiency using the cross-validation technique. This validation method makes sure that the trained model got most of the patterns from the dataset. The best method to do validation is by using k-fold cross-validation. That supports providing ample data for training the model and ample data for validations. Random search. Random search. Random samples are the search space. These evaluate sets from a particular probability distribution. For instance, despite trying to analyze all 200,000 samples, we may check 2,000 random parameters. Bayesian optimization. Hyperparameter setting makes as larger the performance of the model on a validation set. Machine learning algorithms often need to fine-tune model hyperparameters. That tuning is frequently named a black function as it may not be written into a formula since the derivates of the function are unknown. The best way to optimize and fine-tune hyperparameters is by allowing an automated model tuning method by using a Bayesian optimization algorithm. The model used for calculating the objective function is known as the surrogate model. A famous surrogate model for Bayesian optimization is the Gaussian process. Bayesian optimization often works by proposing the unknown function was sampled from a Gaussian process. It enables a posterior distribution for this function as observations are made.